So, uh, so before we start Mahout, let me just touch base on what we discussed last time, just as a closure of that particular topic. So we essentially learned how to invoke map and reduce functions from our client, right? Whether it's RStudio or simply our command line, doesn't matter, but it's from our client. And we primarily used two packages, RHDFS and RMR2, which are from Revolution Analytics company, right? And in RMR, the only thing that's kind of important to remember is that the ability to write R code inside mappers and reducer functions are enabled by the notion of Hadoop streaming, right? Which we already saw how that works. And apart from Hadoop streaming, you simply have to write three different functions, map function, reduce function, and then invoke them using map reduce function provided by RMR2, which will also kind of enable you to create your own key value pairs, your own combiner classes, mappers, and reducers, and so on, right? And before you kind of deal with any implementation, any specific implementation of map reduce algorithm in RMR2, you essentially have to, like, given a problem, you need to think about how you are going to organize your computation in terms of mappers and reducers, right? Because ultimately all your computation is done by maps and reducers, and therefore you have to kind of translate your problem into these functions, whether it's k-means, whether it's any classification algorithm or a clustering algorithm, anything that you want to implement, you need to think in terms of mappers and reducers. And once you think in terms of those functions, you go ahead and implement those functions in R, and then use the RMR's map reduce function to invoke these methods. Okay, so that's kind of high-level approach in dealing with the map reduce from R. Okay, we'll switch gears now and talk about Mahout. Okay, so we already kind of touched upon what Mahout is in several places, I think. First time in the first class, also in a couple of I think 2 classes back or something, where we learned that Mahout is essentially a library, right? As opposed to R, which is a language. And we already talked about the differences between R and Mahout. Okay, so we already talked about the differences between R and Mahout, right? One is a language, one is a library. With language, you can create your own implementations as you wish. Whereas with a library, you simply invoke an existing set of implementations. Okay, and this Mahout is actually started back in 2008 as a sub-project of Apache's Lucene project, which is for kind of data indexing and searching. Okay, and that's why it's used in an open source search engine called Lucene itself. And then they realized the importance of having a library of pre-packaged implementations, and then they started this new project called Mahout, which again is part of Apache, and therefore it's open source. You can download, and most of the Hadoop installations actually come with that, whether it's Cloudera or Hortonworks or IBM or Oracle, whatever is a Hadoop distribution, Mahout is kind of comes with it. Okay, and in Mahout you have prepackaged implementations for a number of algorithms already, starting from clustering, classification, most importantly, recommendations, which we are going to focus on in today's class, and also other data mining algorithms like outlier detections and neural networks, some primitive support for neural networks, and also association rule mining, which is a popular data mining algorithm. So there are several algorithms. We are going to see the list later in the class. Okay, and since this is an open source project and since this is a library, essentially the way it works is whether it's some students or whoever is interested in implementing new algorithms, they would have probably started implementing their machine learning model using mappers and reducers, Java mappers and reducers, not R. And then they kind of donate or commit that particular implementation into Apache Foundation. Okay, that's how a new algorithm gets put into this Mahout library. Okay, and obviously for committing your source code into Apache, there will be some code reviews and there will be some approvals that will take place. But that's how you kind of initiate the process of adding your own implementation into Mahout. Okay, so there are a number of committers already who kind of constantly maintain the existing algorithms and also try to add new set of algorithms to the existing library. Okay, and the most popular one, popular algorithm that is used in Mahout by several companies and several research institutes is the recommendation engines. Okay, which is used obviously to create recommendations for different products or different advertisements or whatnot. Okay, we are going to see how such a recommendation engine would look like and how to implement something like that using Mahout a little later. Okay. So yeah, we have already talked about this. It's part of Apache Foundation, and it has some connections with Hadoop and of course Lucene, because that's where Mahout is coming from. And it has connections to Hadoop because all the implementations are essentially running MapReduce jobs, which are running on the Hadoop and HDFS. Okay. And so again, this is we already know, right? Why Mahout is important, because machine learning itself is important, and not everyone has time and ability to write their own implementations of MapReduce. Like for example, if you want to run k-means, okay, if you don't know, if you're not fully familiar or an expert in implementing algorithms in mapper and reducers, whether it's writing code in Python or R or Java, that's a different question altogether. But let's say if you're not expert in kind of thinking about a particular algorithm in the form of mappers and reducers, then obviously you would look for, okay, is there any implementation of existing implementation of the algorithm of your choice? And then if there exists one, you try to use it, right? And that's what exactly Mahout is doing for you. If you have any popular algorithm that you want to use, you can simply go look into this Mahout library, and if they are available, and if you want to use it as a black box implementation, you can go ahead and use it. And if you want to make any changes, then you go dig deeper into the Java code and MapReduce code to go and make changes. Okay, and that's why as a user, obviously you need to know Java, because the API of all these libraries will be in Java. So you can write any Java application that invokes these functions. But if you want to go ahead and modify those existing implementations, then you need to understand more about the specific implementation and also about the MapReduce coding in Java. Okay, and typically people simply invoke existing algorithms. Not many people actually go. So this is Mahout's website, right? And you can see a list of algorithms that are available today. First one, as I told you, it's mainly recommendation engines, user and item-based, matrix factorization-based recommenders, some algorithms for clustering. Latent Dirichlet allocation is an algorithm for document clustering or topic detection, topic modeling, meaning if you have a bunch of articles, how can I kind of extract the topics that are present in this collection of documents? Okay, that's like a LDA, which is like a document clustering that we have seen using TF-IDF scores. Okay, and there are some classifiers, random forests, naive Bayes. Several times we said something like logistic regression, but we never really looked at what that is, but that's another classifier. And also some Java collections and stuff. So these are all the stuff that are available in Mahout. And one of the web page in that website is called Powered by Mahout, which essentially lists a list of companies which currently use or are trying to use Mahout in their production setting. Okay, and there are a number of popular companies for doing that, including Yahoo, which uses Mahout's frequent pattern mining algorithm, or frequent pattern mining implementation, I should say, instead of algorithm, for doing spam detection in their emails. Okay, and I think LinkedIn also, there should be somewhere some mention about LinkedIn. Yeah, LinkedIn also uses, or they're trying to use Mahout for doing recommendations. Okay, and there are a number of companies, right? You can go over the list. Foursquare, which primarily, I don't know if it's popular in India and other places, but a lot of people in US uses that. And there are a number of other companies which uses different algorithms in Mahout. Okay, so nevertheless, as this one says, the existing implementations are kind of already popular and they will still support and maintain them. So it's kind of useful to know what those implementations are and how they work. Okay, and whatever we learn is not simply about Mahout, but actually a new class of algorithms called recommendation engine. So whether it's Mahout or some other library or some other language, the core concept of recommendation engine will still be the same, and that's what we are going to learn. Okay, so if you see in our entire class, we are not focusing on learning just the tools, but actually the underlying concepts of different algorithms. And using different tools, we are trying to invoke those concepts, right? Like in the case of clustering and classification, like decision trees and random forests, we kind of invoke them through just simply R packages and other things. And similarly, we learned about R and Hadoop using RHDFS and RMR, and we learned what it takes to implement something new. And similarly, in the context of Mahout, I'm trying to introduce you to a new set of algorithms, which are recommendation engine and also frequent pattern mining, which we are going to see again later in today's class. But we are going to kind of invoke those concepts through Mahout. But if Mahout changes tomorrow and something new comes in, those concepts will still be the same, and you can still apply those concepts. Okay, so the goal in this class is to learn different classes of algorithms, and then in your workplace you can find out what class of algorithms that you can kind of utilize. Okay. Okay, so now let's go to the main class of algorithms are recommendation engines, clustering, classification, and frequent item set mining. So we already looked at these two classes of algorithms in the context of R and RMR, and we are going to see about recommendation engine and frequent item set mining. Okay. Okay, let's directly jump into recommendations. Okay, so in the first class as well as in different other classes, we talked a little bit about recommendations, right? Different connotations. We talked about this popular Netflix challenge, $1 million challenge, where you have to develop a recommendation engine that kind of gives more or gives better performance than Netflix company's existing algorithm. And if you can do that, you will get $1 million prize. Okay, but the core problem there is essentially given a set of users and their ratings about movies and TV shows. You essentially have to recommend new set of videos or new set of content to existing users, right? That's essentially the recommendation problem there. And similarly, if you go to Gmail, right? Every one of us go to Gmail every day, and you will see advertisements on the right side or on the top, wherever tooltips, and on the right side also you will see different advertisements. And those advertisements are targeted at you based on the type of emails that you exchange with different people, and the type of web pages that you are surfing in different parts of the web space. So based on all this interactions with Google, they are essentially trying to recommend you some products in the form of ads. Okay, like if you actually so there are many types of advertisements, right? Context sensitive, context insensitive, and so on. Like if you write an email about a particular product, let's say about iPhones or something, and the Google engine actually analyzes that email content, and whenever you are on that email, the advertisements that you will see on the right side will be actually related to your iPhone or the specific thing that you're talking in that email. Okay, so that's like a context sensitive recommendation, where depending on the context, which in this case is an email that you're writing or which you're reading, based on that, it's kind of giving you recommendations. Okay, so you'll see recommendations everywhere. Take the example of Amazon, right? We all go, at least in US, we all use Amazon, and based on the products that you're browsing, they try to recommend more stuff to you. Okay, so the bottom line is recommendations are everywhere, and that's the way people are trying to encash all the social interactions, all the interactions that you're doing on top of web, whether it's social media, whether it's web search, whether it's browsing histories, and so on, right? Another example that we talked about is YouTube videos, right? Depending on the video that you're watching, or depending on the videos that you've been liking and commenting on, it tries to give you more recommendations. Okay, so and Mahout has a pretty sophisticated support for doing building recommendation engines. Okay, and it all started from something called as taste framework, developed by a person called Sean Owens, Seanowens. So this guy was working on this taste framework for doing some recommendation engine, and later on he kind of donated that code to Apache Foundation, which kind of made its way into Mahout as a recommendation library. Okay, and as the name suggests, this framework, taste framework, essentially takes the tastes of different users into account. Right, depending on their taste, you are trying to recommend new products and new items to those users. Okay. Like in this slide, it talks about a site sells books or CDs, could easily use Mahout to figure out from past purchase data which CDs a customer might be interested in listening to. Okay, not very surprising. That's how the recommendations actually work, right? And I said recommendation engines in Mahout is pretty sophisticated because it's not just a simple implementation of a particular algorithm, but it actually a framework containing different components, and using these components you can build your own recommendation engine. Okay, so it's already little more than what a simple library is. Okay, whenever I talk about library, it's simply a function that you can call, right? Whereas the recommendation engine in Mahout, yes, it's a library, but it's little sophisticated library where you have a bunch of components and you put together different components one after other, and then you suddenly get a new recommendation engine. So the combinations are kind of multiple. Okay, we are going to see what those components are, what they mean, and how do you kind of put together to create a recommendation engine. Okay, and if you just intuitively think about recommendation problem, okay, you can already come up with simple ways of doing it. Okay, which is, so let's say I'm recommending movies, okay, to, let's say, Rajiv. Let's say we want to recommend some movies to Rajiv. How would you do it? Okay, if you think about it, it's pretty intuitive that, okay, if he's watching a lot of action movies, then probably we will recommend some action related movies or some thrillers throw in there. Or if he's watching a lot of comedies, then we'll probably show him comedies. Or if he's watching a lot of movies from a specific director or a specific actor, then we'll again take those aspects into account and recommend appropriately, right? That's one way of doing it. And the other way of doing it, okay, before I go into the other way, what essentially we're saying is, depending on what items or products that he has been using in the past, we're recommending more products to him, right? And in this case, products are movies, and by using the product, I mean he's watching that particular movie or TV show. Okay, so that's basically item-based recommendation. Depending on the type of items that Rajiv is interested in, or that Rajiv has been using it, you are recommending more stuff. Okay, so all your logic is kind of focused on the items. And there's alternatively, there's other way of looking at a recommendation problem, right? There may be many other people in your customer base who are like Rajiv, okay? Which means, so obviously in your customer base, there will be multiple customers who are kind of have similar taste, okay? And you can recommend certain products to a person based on what others are using or others are consuming, right? So you essentially try to find a person who is similar to Rajiv and then take all the products that the other person is using and then recommend them to Rajiv, right? That's how, that's another way of doing recommendations, okay? So that's basically a user-based recommendation. Essentially, you are trying to recommend some products based on the similarity between the other users and the current user to whom you are trying to recommend. Okay, do you see the differences? Okay, one is a user-based recommendation, other one is a item-based recommendation. So this one is essentially telling why recommendations are important. That's not really technical enough for us. Some use cases. Okay, so that's about the basics of recommendation engines that are available, or the most popular recommendation engines that are available in Mahout. One is user-based recommendation, one is item-based recommendation. Okay, we are going to see some more technical details into that, but and as you can see in the slide, there are also other methods like factorization based and several other methods. And all these recommendation algorithms are kind of collectively called as collaborative filtering. Okay, that's another terminology that you typically hear in the context of recommendation engines. Okay, and we already talked about other class of algorithms available in Mahout. And so if you actually open up the source code in Mahout, and these are the high-level packages that you will see. So this is a top-level package, arc.apache.mahout, and one core package within this is essentially Mahout core. Okay, it's essentially the library of different algorithms, classifier, recommenders, data mining algorithms, clustering algorithms, and so on. And they make use of other packages like Mahout Math. Okay, we already talked about linear algebra being the fundamental to many machine learning algorithms, right? Like, for example, k-means you can actually implement using linear algebraic operators like matrix multiplications and matrix cell-wise operators and so on. And similarly, you can express other algorithms like linear regression, logistic regression, support vector machines, all those things using linear algebraic operators. Okay, so obviously, for different algorithms, you don't want to implement these basic operators again and again. So you put all of them together into one package called Mahout Math, and you develop algorithms using those core data structures and operations on those data structures. Okay, and similarly, you have Mahout collections, which are typically like Java collections that you probably are aware of already, like lists, hash maps, arrays, linked lists, and so on. Okay, so if you are familiar with Java, for example, if I want to construct an array list of integers, okay, I won't use the primitive data type int, but instead I have to use an object or a class, integer class, right? Capital I integer, right? That's the class I would use for creating collections. Okay, and that means whenever I want to create a new item into, or whenever I want to add a new item into that array list, I have to create this integer object and then add it to that particular array list, right? That's how typically you do in Java. But there is a significant overhead using those collections because these objects have internally a lot of memory overhead, right? In order to avoid dealing with these complex objects for using simple array of integers and hash map of integers, they essentially came up with better implementations of these collections using primitive data types. Okay, so in here, ArrayList can simply take primitive data types like int, float, and double, and so on. Right? That's essentially the thing that is offered in this Mahout collections. Again, you don't need to know them, but if you want to implement a new algorithm, you can actually go ahead and use these Mahout collections, which are essentially a better implementations than what you get from Java Lang package, for example. Okay, and there are some examples in Mahout examples package, and there's also an important package called Mahout integration. Okay, this essentially has different interfaces or adapters to kind of communicate with different data processing systems. So let's say if you want to import data from a database and then run your machine learning model on that database data. Okay, so you can use some tools available in this Mahout integration package. Or if you have data in different formats, somebody talked about Avro format. There are many other data formats, right? In order to kind of consume data which is represented in those formats, you use different adapters or interfaces available in Mahout integration. Okay? And similarly, there's Mahout utils and several others. These are the more important packages in Mahout. Okay? Any questions? Yeah, I'm just going through this so that you kind of get a sense of what is there in Mahout. It's not just the library, which is obviously the most important one, but also some primitives for linear algebra operators on MapReduce, and also like Mahout collections, which are actually usable in any Java application, right? Whenever you want higher performance of those collections, you can kind of use these existing implementations. Okay? And in Mahout, as I was telling, recommendation engines are a little more sophisticated, and they are composed of different components. Okay, and these components are typically or primarily the key abstractions that are realized using different interfaces. Okay, the first one is a data model interface, which is essentially kind of adapters to different data formats, right? How do I, so this interface is responsible for kind of importing data from different data sources or the data in different formats into the data structures which are used by other interfaces which are actually doing the recommendations. Okay, so this is like the data import and export portion of recommendation engine. Okay, and there is interface for user similarity, like we talked about a possible implementation of a recommendation engine based on the similarity between users. Okay, we'll look at the details, but this particular interface essentially gives different mechanisms in which you can measure the similarity between users. Okay, in the example that we talked about, like we want to recommend some movies to Raji, and in order to do that, we have to find which all other users are similar to Raji, right? And before even we talk about finding similar users, we need to know how to compute such a similarity, right? Given two users, you need to be able to compute the similarity between them. And this particular interface has different methods available already for doing something like that. Okay? And similarly, there's an item similarity interface, which is responsible for computing the similarity between different items. Okay, and there's something called user neighborhood interface. So, for example, if I want to again recommend some movies to a particular user, instead of looking at all the other users in your customer base and then recommending to this particular user, we want to focus only on most similar users, right? Out of 10,000 users in your customer base, we may want to focus only on, let's say, top 10 users which are similar to a particular user, right? That means we are talking about some kind of a neighborhood around a particular user, and based on the items that are purchased by that neighborhood users, we are going to do the recommendations. Okay, so this interface essentially gives methods to construct a neighborhood around any given user. Okay, and ultimately there is a recommender interface, which is essentially methods to make actual recommendations. And then you can build your own recommendation engine by kind of composing different methods from these different interfaces. Okay, that's why I told recommendations engines are not just library, but a little more sophisticated than that, because each of this interface is giving you a different set of methods. Okay, and then you kind of pick and choose one method from each of this interface, and then you can compose a recommendation engine that is kind of custom made by yourself. Okay. Okay, so data model interface, as I told, it essentially about import and exporting of data from different data sources. And in this particular case, supported data sources are different databases, MySQL, PostgreSQL, CSV flat files, and also other NoSQL databases. Probably you heard about these names in different contexts, like MongoDB, Cassandra, and so on, right? And essentially, you import data from all these data sources and kind of convert them into internal data structures, okay? And internally, all your data is represented in this format. It's essentially triplets of preferences, okay? And each triplet contains these three components: user, item, and the rating. As simple as that, right? In case of Netflix, for example, user will be different accounts on Netflix, and the items are movies, and the ratings are essentially how much rating a particular user has given to a particular item. Okay, so this is called a preference. So you essentially import data from your data sources and then represent them in the form of these triplets. And you kind of have more complex data structure for every user. Okay, there's a user ID, and there are a bunch of item IDs that user has provided preferences for, and accordingly for each of those items you have the corresponding preference value. Okay, so that's what is called user preference array. Now, independent of your data source, you kind of import the data and store them in this data structures, user preference array. And then your subsequent algorithms for computing similarities between users, computing similarities between items, and every other algorithm will be operating on this particular representation. Okay? And for user similarity, there are many methods that are already implemented for you, starting from Pearson correlation, Jacquard similarity, cosine similarity, which we already talked about. You can even compute Euclidean distance, Manhattan distance, and many others, right? So these are all are already available to you. Okay, whenever you invoke a recommendation engine, you simply have to specify which similarity measure that you would like to use, and that's all you need to do. Okay, so these are the methods that are available to compute the similarity between different users. Okay, and similarly there will be the same methods or some of these methods can be used for computing the similarity between items as well. Okay, and for the user neighborhood interface, essentially as we are talking about, for doing recommendations, you don't want to look at like entire data to give recommendation to a particular person, right? Instead, you want to focus only on the relevant subset of data, and that relevant subset can be the most similar items to the ones that you have already seen, or the most similar users which are relevant to your specific customer. Okay, that means if I want to recommend it, movies to Rajiv, then I look at only, let's say, top 10 most similar users that are, or top 10 users which are most similar to Rajiv, right? That's one approach. You essentially, out of all your customer base, you are taking, let's say, a nearest n users. So I want to recommend movies to a user U1. Okay, out of all the users, I select the top 3, and then I focus only on these top 3 in order to make those recommendations. Okay, so that's one approach of constructing a neighborhood around a particular user of interest. Okay, and the other one is basically a threshold-driven method, which is essentially says, out of all the users, I take those users whose similarity is greater than, let's say, 80%. Okay, that means I'm kind of creating a neighborhood based on the amount of similarity that I have. In this case, we simply take top 3, whether the third top is maybe only 50% similar. We don't care. As long as it's in top 3, we are going to use that particular user's data. Whereas in threshold driven, you are doing it based on the actual similarity value. Okay, so these are just 2 different methods in which you can construct a neighborhood around a particular user. Now, once you construct that neighborhood, you simply take all the data from these different users and then make recommendations for the particular user of interest. Okay, and finally, as we said, there is a recommender interface, which is essentially says, given a data model, that means your import and export scenario. That means, let's say you have data in MySQL database and you kind of select a particular adapter to import data from MySQL database. Okay, so that's given by your data model interface, right? So given a particular data model and a given definition of similarity that you would like to use between users and also items. Okay, and also a given definition of your neighborhood, user neighborhood, which is essentially one of these 2, right? Given all these 3, the recommender interface is essentially produces an estimation of relevance for each of the unseen item. Okay, this is essentially the recommendation that you are creating for that particular user. Okay, and there are many methods of doing such recommendations. And these are all the methods that are implemented currently in Mahout. Okay, so essentially what you have is these different interfaces and multiple methods for each of that interface, and you simply, as a user, you pick and choose different methods from each of those implementation interfaces, and you can kind of compose your own recommendation engine. Okay, I'll show you an example of how that looks. Let me go back in here. Okay, so this is an example of user-based recommendation, recommender engine that I'm constructing. Okay, first, as I told, we'll have to decide on the data model. Obviously, that depends on where your data is. And in this example, I have data in a CSV file. So I create a data model which kind of connects to that particular CSV data. And if you have a data in a particular relational table, you will create a data model that kind of connects to the database and gets the data. Okay, and I'm creating a similarity measure, and in this case I would like to use Pearson correlation similarity. Okay, and for that I'm providing my data, obviously, because only from this data I can compute similarities. And then I'm defining a notion of user neighborhood, and in this case I would like to use nearest n neighborhood. Okay, as opposed to threshold method, I want to use the nearest n. And then using these three, that means the data model, user similarity, and the user neighborhood, I can now create something called recommender, which is the recommendation engine that I am building by composing these different methods. Okay, now using this recommender object, I can simply create new recommendations for different users. Okay, so that's how an implementation of a recommender engine would look like using Mahout. Okay, so that means tomorrow in your workplace, if you want to create a recommendation engine for your own program, for your own data, then this is how your Java program would look like. You first define a data model that kind of interfaces with your data source, and you define what is the similarity measure that you would like to use. Okay, that's something you need to decide. For this application, this is a similarity measure I would like to try. Okay, and again, as we talked in the context of k-means, there's no clear set of rules which tells you, okay, this is the way this is the way a particular similarity has to be measured. It's completely depends on the data and the domain, so you kind of try out a bunch of things and see which one works better. Okay, and similarly you define a notion of neighborhood. Okay, and using those individual components, you build a recommendation engine, and then use it subsequently for doing the actual recommendations. Okay, this is all you need to do as a user, and everything is done underneath, under the hood for you. So these are the components. I mean, we talked about these are the. This is how a recommender engine would look like in Mahout, right? And we already talked about this user-based recommendation engine, and similarly there is a item-based recommendation engine. Okay, so instead of figuring out what to recommend based on the most similar users, you can kind of figure out those recommendations based on your past history of that particular customer, right? So in this example, user 1 already like purchased multiple items, in this case fruits. So user 1 bought 3 different fruit, and user 2 bought 2 different fruits, and user 3 bought 1 fruit. Okay, now given this data, you need to recommend some fruits to a particular user, user 3. Okay, how would I do that? In the context of item-based recommendation, I essentially construct an all pair similarity between all the items. Okay, what is the similarity between first fruit and the second fruit, first fruit and the third fruit, first fruit and the fourth fruit, and similarly between 2 and 1, 2 and 3, 2 and 4, 3 and 1, 3 and 2, 3 and 4, and so on. Okay, between all pair of items or all pair of fruits, I am going to construct a similarity value. Okay, so I get a, if I have n fruits, then I have n by n matrix, right? That's a similarity matrix. Now, using those, so I know that user 3 already bought fruit number 3. Okay. Now, by looking at the similarity of that particular fruit with all the other fruits, I can kind of get a top list of choices for making recommendations, right? Let's say fruit number 3 is very close to fruit number 2. Okay, in this case, probably a strawberry here. And if that similarity is very high, then I can say that, okay, this particular user has already purchased this, so he might also like fruit number 2. So you go ahead and recommend that. Okay, and you basically do like that. Depending on how many recommendations you want to do, you keep looking at these item similarities and then make recommendations. Okay. So, as it says concisely here, item-based recommendation is derived from how similar items are to other items. Okay, instead of looking at the similarity between different users. Okay. So, in Mahout, all that means is instead of taking a user similarity, you take item similarity. Okay. So, for example, we have already seen this one, right? So here I'm constructing a user similarity value. I call it specifically the Pearson correlation. Instead of constructing the user similarity, I construct an item similarity and then simply pass that item similarity to my recommender engine. Then it suddenly becomes an item-based recommendation. Okay? Yeah, so we already talked about this, right? You essentially constructed all pair similarity between all the items. Okay, so in this video 1 has similarity with video 2, video 3, video 4, and also other ones. You construct those all pair similarity, and then subsequently you use those similarities to make the recommendation. Okay. Okay. So this one essentially tells you little more detail about how an item-based recommendation would look like, right? So here we want to recommend certain items to a particular user U. Okay, so the way it works is for every item I, that user U has no preference yet. Okay, so this U would have probably given ratings to a bunch of items already, and there will be other items which don't have any rating by U, right? Obviously, you have to recommend only from that subset, right? That means if I already watched a particular movie and I rated it, I don't want to recommend the same movie to him, right? Because he already watched it and he also rated it, okay? And that's why you are essentially taking all those items for which he did not specify a preference or he did not watch it, okay? So for every such item, and also for every item J for which the user has already provided a preference for, okay, and you compute the similarity between those I and J, okay. If you already pre-computed your all pair similarity matrix, you simply fetch a value from that matrix to get the similarity between I and J, okay. So again, item I is something that the user has not seen so far or user has not purchased so far. So it is a candidate for making a recommendation. And then item J is something that the user has already seen or purchased. Okay, and you are computing the similarity between I and J. Okay. Okay, so let's go to our Hadoop installation, which is on my VM. Okay, so I'm on a virtual machine where the Hadoop is already installed. Okay, and if it's a Cloudera distribution or any other standard distribution, as I told, Hadoop will already be available. Mahout will already be available to you, and which you can find by simply saying which Mahout. It will tell you where the Mahout executable is present. Okay, and if you simply type in Mahout, it tells you the list of all the algorithms that are available. Okay, can everybody see this? Is the font size okay, or should I increase it further? Okay, so whenever I simply type Mahout, I get the list of all the algorithms that are present in Mahout, and these are all like the commands that you can provide to Mahout library. Okay, let's just quickly go over that just to get a complete picture about Mahout. Okay, so there is something for clustering, approximately how many in Mahout. So again, these are all the ones. Actually, some of them are not really algorithms. They are simply some building blocks. Like for example, this one, it's more like a utility, right? ARFF is a specific file format used in, I think it's from a tool called Weka. Just like R, Weka is also another tool for doing machine learning. And ARFF is, I think, the data format used by Weka. Okay, so this particular utility, ARFF.vector, is simply for generating vectors from ARFF data. Okay, so these are all the things that are available, but some of them are not really algorithms, but they are simply some utilities that to do more stuff. Okay, and so that's just a utility, and this one is for HMMs, hidden Markov models, which are typically used in applications like speech recognition and so on. So HMM is a huge class of algorithms, just like clustering and classification. And the specific algorithm that is being implemented here is Baum-Welch algorithm, if you are interested in that. And there's one, this is for clustering, just like k-means and TF-IDF based clustering. Canopy clustering is another method for clustering. Okay, if you are actually familiar with SPSS, this is a primary method that is implemented in SPSS suite of clustering algorithms. Okay, this again is another utility. There's some support for SVDs, singular value decomposition, which is like a dimensionality reduction technique. Okay, I think we talked a little bit about what dimensionality reduction means, right? Essentially, in your real world examples, real world problems, the number of features that you have will typically be very, very high. Okay, and a lot of algorithms will not scale very well in terms of performance and in terms of convergence to large number of dimensions. Okay, in those cases, you try to come up with a smaller subset of features which are most important for your data. Okay, and things like and that's where the dimensionality reduction techniques come into play. And one popular example is singular value decomposition. And there's another popular example called principal component analysis, or PCA. Okay, so this is one algorithm for doing that, which is supported in Mahout. And there's some other utilities, and this another clustering algorithm, fuzzy k-means, which we already said what that means, where, so in your regular k-means, every point belongs to a single cluster, whereas in fuzzy k-means, each point can belong to multiple clusters. Okay, so it's like a soft clustering as opposed to hard clustering. Okay, the popular example that we talked about was like if you look at different users and their interest. Again, let's say Netflix example. A particular user may be interested in not just in action movies, but also in comedy movies, right? So if I want to cluster my user base based on those interests, then a particular user may belong to multiple clusters. One is action cluster, another one is comedy cluster. You cannot accomplish something like that using k-means, right? Because each point in that case, in k-means, each user is kind of forced into a single cluster. Okay, so you choose between action and comedy, whatever is the most interesting genre for that particular user, that's what you will use. So it's like a hard clustering. And fuzzy k-means is like a soft clustering. Okay, and there's algorithm for frequent pattern mining, which we are going to see next in today's class, and some other HMMs, item similarity, which we just talked about, compute item similarities for item-based collaborative filtering. Okay, and there's k-means already, so you can run k-means, which is implemented in MapReduce using Mahout. Okay, and as we talked before, it was coming from Lucene, so it has some utilities related to Lucene indexing structures as well, and some other utilities. This is another collaborative filtering algorithm or a recommendation algorithm, alternative least squares, ALS. Okay. Again, another recommendation algorithm, factorized algorithm, and recommend item-based recommendation, and bunch of things like sequence jumper. These are all the utilities. Spectral k-means is again another class of another clustering technique. Okay, SPD, we just talked about it, singular value decomposition, which is a dimensionality reduction technique. And there's naive Bayes algorithm for classification, which we already learned in this class. There's logistic regression, which is again we mentioned several times, which is a classification algorithm also. Okay, and there are several others, right? You can like go to our Mahout webpage. You can see basics, list of all the algorithms. Okay, actually this is probably a better way to look at the list as opposed to from the command line. So there is collaborative filtering, okay, which is for doing recommendations. Okay, there's user-based, there's item-based, there's factorization-based, and weighted matrix factorization, some other techniques. Okay, and there are a bunch of algorithms for classification, logistic regression, which we mentioned several times, naive Bayes we learned, random forest we already learned, and hidden Markov models, as I was talking about, it's primarily used in things like speech recognition, but there are other applications as well. Multi-layer perceptrons, which are like neural networks, if you heard about that particular class of algorithms. And a bunch of methods for clustering, canopy, k-means, fuzzy k-means, streaming k-means, where the data is coming in as a stream, right? And so how do you cluster those streaming incoming data points? Spectral clustering is another type of clustering which depends on some graph-based techniques. We just talked about what dimensionality reduction means, right? How do I go from this massive set of features down to small subset of important features in the data? Okay, there are a bunch of methods, PCA, SVD, and so on. Topic models, which we again talked about. How do you construct, how do you extract topics from a given set of documents? Okay, that's like topic-based clustering. You can think of that way as well. That is one algorithm called LDA, and other data mining algorithms like frequent pattern mining and so on. Okay, so I mean, I'm just simply kind of throwing out names at you. I don't expect you to understand all this, but just to kind of give you a sense of what are all things available in Mahout, right? Some of you may be familiar with classification algorithms, whereas some others maybe are familiar with clustering and so on, right? But just to give you a complete idea of what all are supported in Mahout. And if you see, we are kind of learning some class of algorithms from each of these subsets. We learned about classification, we learned about clustering, we are learning about collaborative filtering. Dimensionality reduction, we don't see anything, but we are going to see later on about frequent pattern mining and so on. Okay. Okay, let's go ahead and try to run a recommender engine. Okay, so we are going to look at a data set which is similar to the Netflix example that we talked about, called movie lens data. Okay, so movie lens data is a publicly available data set which kind of has a similar structure as Netflix data set. So you can actually just Google that and you'll get this particular web page, movie lens. Okay, and there are a bunch of data sets with different sizes, 100K, 1 million, 10 million, and so on. And if you look at it, it's essentially data collected through movie lens website. This particular data during the 7-month period from September 19th to April 22nd. Okay, essentially it has a bunch of data sets, but the most important one, the one that we are going to see, is this, which is 100,000 ratings given by 943 users on 1682 items. Okay, so we are going to see this, we are going to use this data and then kind of make recommendations for different users. Okay, and let's, I mean, we can do both user-based and item-based, but let's start with something and then use Mahout to do recommendations. Okay, so I already downloaded this data from this particular website. So that's in my folder here. Data ML is movie lens, 100K. Just since it's a example, I downloaded the smallest data, and these are all the files that I got. Okay, the one that we are going to look at is this u.data, which is essentially the username, item name, or user ID, item ID, and the rating and the timestamp. Okay, that's what is there in the README as well. If you see u.data, it's user ID, item ID, rating, and the timestamp. Okay, so we are going to use this data to make recommendations, or to build a recommendation engine and then make recommendations. And the other data files are essentially some information about users, some information about items, different genre that the user likes, and so many other things. Okay, for the example that we are going to see, we don't need all that information. So as we said that already, these are all the stuff. And let's start with item similarity or recommend item based. Okay, let's try to build item-based recommendation engine and then make some recommendations using that engine. Okay, so we need to pass recommend item-based as an algorithm. Okay, Mahout recommend item-based. It's going to tell us what are all required. And for this, we need to specify a bunch of things. Okay. Input file, output file, number of recommendations that you want to make for each of the user. Okay, and these are all some optional parameters: users file, items file, and bunch of other things like maximum preferences per user, minimum preferences per user, and more importantly, what is the similarity class that you want to use. Okay. Like, do I want to use cosine similarity, Jacquard similarity, Euclidean similarity, and so on. And the supported similarity classes are right here. Okay, name of distributed similarity measures class to instantiate, and they can be based on co-occurrence, log likelihood, Tanimoto coefficient. City block is the Manhattan distance, cosine similarity, Pearson similarity, Euclidean similarity, and so on. Okay, so let's run it on our data. Okay, before I do anything, I need to copy my data to HDFS, right? Because that's where the Mahout is going to get the data from. And in this case, I already copied. So let's look at that. fs minus ls data. Okay, movie lens. Okay, that's the data set we are interested in. Okay, u.data. Okay, that's on HDFS. So we are going to use that data and make some recommendations. So Mahout item, what was that? I recommend item based minus input data / movie lens / u.data. Okay, that's the input file, and then we need to provide output file as well. Data movie lens, and then let's say item recommendations. Oh, that's my output file, so I need to specify minus output. Okay, and we need to specify a similarity measure, right? And that's given by minus similarity class name. And let's use something, let's say Pearson correlation, or yeah, Pearson correlation is fine. Okay, and let's say we create 5 recommendations for every user. So I'll say num recommendations is 5. Okay, so what essentially I'm trying to do is I'm doing an item-based recommendation engine on this input data, and my produced recommendations are going to go in this particular file, and the similarity measure that I'm using is this. Okay, and the number of recommendations I'm creating is 5 for every user. So when I execute this, it essentially going to do a bunch of things like we saw before. It computes the all pair similarity between different items. Okay, and then for every user, it tries to compute 5 recommendations. Okay, so it's not like for one particular user, for a given user, instead of providing recommendations for a given user, it tries to provide create recommendations for all the users. Okay, this is a command line invocation, but typically you want your recommendation engine to be kind of integrated into any other application. Then you would go and create something like what we have seen here. Yeah, you would create something like this. Okay, so you not just batch mode, but you can create recommendations per user as well. And in those cases, you would write something like this. You create a recommender engine, okay, and then you pass the user for which you want to create recommendations to this particular object, okay. So this object takes up has a bunch of methods, and one of the method will take a given user, and then it provides you a list of recommendations for that particular user. Okay, but from command line, you would create recommendations in a batch mode. Okay, so let's go ahead and run this particular command. Oops, it says file already exists. So it creates some data files into some temporary location, and the temp folder already exists on my HDFS, so it's complaining. So let me remove that. Hadoop -fs -rmr temp. Oops, no folder. Then why is it complaining? Okay, let me go here. Cloudera. Oh, I think it's /temp. Sorry. One second, I'm trying to see what this. Oh, I see. Okay, I think the issue is that. So, okay, before I explain this particular exception, let me talk about this flag called Mahout local. Okay, what Mahout local says is, so in the context of Hadoop also, we have seen like R and Hadoop, there's something called mode, which tells you whether to execute something in local mode or in like true MapReduce mode. Okay, similarly, when I set Mahout local, that means I read data from local file system and I produce data into local file system. So it's kind of executing in the local mode. And you do that typically for quick prototyping. Okay, it's not really running in parallel, but instead of running in parallel, you are running it on a single machine. And for the demo purpose, I set that particular flag to true. And if you do not have that flag set, then you will actually run real MapReduce jobs. Okay, and that will take a long time because this item-based recommendation runs like 9 or 10 MapReduce jobs, one after the other. So which will take a long time to run to show in the class. So I set Mahout local to be true, and whenever it is set, it tries to look at the data from your local file system. And if you see my file system, there is something called temp directory, and it's complaining that the temp is already exists. So I need to remove that temp before I run anything. Okay, so I'm removing the data from my local file system. Come on. Okay, so my temp directory is gone now. Now I can run again. Probably it will complain about the output directory as well. Okay, input part does not exist. My input is essentially my current directory, so I don't need to do all this. So since I am in local file system, I'll have different path. Okay, so I'm taking my user data from the current folder ML100K, and then I'm creating this output recommendation engine, output recommendations, similarity measure, number of recommendations, right? It will probably complain about the output folder as well because I have that already here. So let me remove that as well, minus rm output. Now I can run this. Okay, is that clear? I'm taking user u.data from my current directory and I'm creating this output recommendations in this output folder. Okay, let's run that. And since the Mahout local is set, it's running everything locally. Okay. If that flag was not set, the data would be reading from HDFS, and it will generate a lot of MapReduce jobs to do the actual computation, and it will produce the result in the specified folder. Okay, as you can see, even the local mode is kind of already taking a little bit of time. Okay, so it's finished. Now if I do ls, I again see two folders, my temp folder as well as the output folder, and obviously we are interested in the output folder. Okay, there is the item records that we just did, and you can see the list of recommendations. Okay, so this is for user 1. Okay, for user 1, it is recommending 5 items, and the items are 1652, 1646, 1644, 4229, and the projected or the predicted ratings for these items are 5.0. Okay, and similarly, if you look at the user number 17, for example, the recommended items are 762, 1327, 1170, and so on. And after colon, you will see the predicted rating for user 17 and item 762. Okay, so if you actually go to your items data, which is u.item, okay, you will see different items here. So if you go to 762, that movie is actually called Beautiful Girls. Okay, so that's the movie that was recommended to that user number 17. Okay, so similarly, you will see top 5 recommendations for all the users in your database. Okay, and that's why Sanjay was referring to this as batch mode, because you are creating recommendations for all the users in your data. And this is also kind of useful probably in practice, because like as a Netflix service, I may not want to do all this processing for every user on the fly, right? I need to kind of pre-compute some of my results, and I simply show those results whenever the user requests for it, instead of start computing it. Okay, So even this batch mode recommendations probably make sense in practice, right? But if I want more on-demand recommendations, then I have to kind of directly call the Java API that we have seen. Okay, so what we did is simply we used the movie lens data and we called or invoked the item-based recommendation engine that is present in Mahout. Okay, using a particular similarity measure called Pearson correlation. Okay. So typically you don't show them the recommendations because they don't make sense out of it. Like as I just showed you, what we saw is this, right? We can't just show this thing to the management or even the decrypted names. Like even if I replace this 743 with the appropriate movie name, still it doesn't make sense to management because they don't care, right, what that movie is. Instead, you actually, just like for classification algorithms, we computed things like recall, precision, false positive rate, confusion matrix, and all those things, right? So similar to those metrics, even for recommendation engines, you can kind of build those metrics and then present those metrics to the management. So that's actually the last slide I had. Yeah. Evaluation of recommender engines. Okay, so typically the most common things used are this mean average error, RMSE. Probably you heard about this RMSE in several other places as well. Root mean squared error. Actually, if you look at Netflix challenge, you typically see these RMSE values posted by different contenders in that particular challenge. It's essentially, as the name suggests, it's a root mean squared error. You compute the error, you square it, you take the average of all the squared errors, and then take a square root of it. Okay, that's why it's called RMSE. And And also, some people use things like precision, recall, F measure, just like what we have seen in the classification algorithms. So these are the metrics that you would compute for the recommendation engine that you built, and then show these results to your management. Okay. So even for this, just like we did in classification, you kind of divide your data set into training set and testing set, and then you compute these metrics using your testing set. Okay, error for a recommendation engine is essentially the difference between the ratings that are actually there and the rating that you predict. So in this, we have seen like in our result file, for every item, like here for item 1658, the predicted rating is 5, but actually there must be some actual rating, right? If you divide it into a test set, because test set gives you a ground truth and this is a predicted value. So you take the difference between the two and you get a error value. Okay. If Amazon recommends an item, does it also predict what my rating for that item will be? So it may be under the hood, because I mean, I don't know particularly what the specific setup Amazon has. It may have, but it's internal, right? You don't see it. When I recommend my items to this user number 489, I simply give him 1658, 1656, 1646, and so on, those items, but not really these ratings, right? So user may not see them. Probably internally they will have some scores, It may not be the interpretation of rating, but they will definitely have some kind of a score. Okay. So once Amazon recommends you a product, in order to get the evaluation or get the effectiveness of that recommendation, they can kind of look back later on. So after a couple of days, probably they'll look at their data and say that, oh, okay, I recommended this particular item to Sanchit, but he didn't really buy it. So probably there'll be some kind of feedback loop which may go on later on, but that's again making it a little more complex. Okay, so what we are going to talk about is something called association rule mining, also called pattern mining, also called item set mining. There are many names of it, but the most popular ones are association rule mining and frequent pattern mining. Okay, this is, so whatever we have seen so far, like clustering, classification, all those things are a lot of math behind it, right? A lot of statistics, or a lot of math optimization functions and stuff like that. Whereas this one, association rule mining or frequent pattern mining, is simply based on counting. Okay, there's no I mean, there is some math aspects to it, but the core algorithm is simply based on counting. Okay, we'll see what exactly is being counted and how those counts are used. And so just to give you a quick introduction, association rule mining is proposed by a researcher called Rakesh Agarwal. Back into 1993. He was one of the pioneers. There are obviously a couple of others as well. Back in 1993 when he was in IBM. Now he's at Microsoft, I think. Yes, Microsoft. And this particular technique is also called as market basket analysis. And primarily because of the application in which he kind of proposed this technique. Okay, so let's quickly see what that application is, just to give you an idea of what this technique can do. Okay, so at least in US, whenever you go to, probably even in India, in all the supermarkets, you have this notion of a membership card, right? If I go to, like in US, if I go to a Kroger or Walmart or Safeway or whatever is the local grocery store, you have this membership card. If you use that, you get some discounts and you get some coupons in email, in your mailbox and so on, right? But what they actually do is, whenever you use this membership card to make a transaction, they log that particular transaction, saying that, okay, so-and-so user bought, these are the list of items in this particular transaction at this point in time at this store and so on. All that information will be logged against your membership card. Okay. Now, obviously, you will visit that particular grocery store again and again over the time. So you have a list of transactions that are logged against you, okay, which tells you what is your purchase history for in that particular store. And similarly, all the customers who use those membership cards will have their transaction history. Okay. Now, as a company, as a Walmart, for example, actually Walmart is also a pioneer in in applying this particular technique in practice. So whenever you see or whenever you read about this particular technique, you will see a lot of references to Walmart. So as a Walmart company, I have this enormous amount of transactional data, okay, where each transaction is a set of items, right? I go to grocery store, I pick up a bunch of items, and then I buy them all in one transaction, okay? So my transaction contains a bunch of items that I bought in that particular transaction. Okay. Now, by looking at all these transactions, what this market basket analysis says is it tries to find the most frequently bought together items. Okay, it will try to find things like, oh, okay, whenever I buy milk, I also buy bread, for example. Okay, so that's kind of the stuff that is output by association rule mining, and it's called association rule because it's trying to extract the association between different set of items. Okay, so the example association is something like this: bread implies milk. That means if I see bread in a particular market basket, okay, then I can, with some confidence, I can say that that basket also contains milk. Okay, does that make sense? So the existence of bread is implying something about the existence of milk in that particular transaction. Okay, and how much probability or how much chance that milk exists is something called as confidence. Okay, in this particular example, whenever I see bread in the basket, with 100% confidence, I'm telling you that milk will also be there. Okay, that's what is the output of this particular algorithm. We'll see why that is important, why such a rule is important, but do you understand the notion of association rules? Okay, let's see how they are actually used. So, what is the use of such rule, right? Why should Walmart extract or mine for such rules? Okay, one basic use is the item placement in the store. Okay, in your Walmart store, how should I decide where to place bread and where to place milk? Okay, they have to be in some aisle, right? So how do I decide that? This is something that I can use to do that placement. So I see that bread and milk are most often bought together, and actually with 100% confidence, bread implies milk. So I can actually place both bread and milk together in one place. That way customers can kind of pick both of those items in the same place, instead of going round the corner to a different place in the store to buy to pick that particular product. Okay, so one obvious use is positioning of the product, and another obvious use is recommendations or giving coupons. Okay, so let's say I want to promote the sale of milk product that I have in the store. Okay, then what I can do is I give you some discount on bread, so that you pick up bread and you indirectly pick up milk as well with some confidence, right? So you can kind of promote different products or give coupons on different products using those association analysis. Okay, so that's like a product sale, essentially. That's another area where you can use those analysis. Okay, and other one is something called as price elasticity, meaning if I want to increase price of bread, I can analyze how that will impact the price of milk, for example, because bread implies milk, and therefore if I kind of increase the price of bread, probably people don't buy bread anymore, and therefore the milk consumption is also goes down, right? So those are the kind of cross elasticity or price elasticity that you can analyze using those associations. Okay, so there are many applications in retail world which kind of relies on these associations, and the notion of association rules exists in many other domains as well, but it's more popular in the retail area because that's where they were invented from. So if you think about it, it's completely different from what we have been seeing so far, right? In the clustering, we talked about, how do I group or how do I segment my data into different clusters or segments. Whereas in classification, we were talking about how do I predict some class label, whether it's spam, no spam, fraudulent, not fraudulent, and so on. And in recommendations, we are looking at how do I recommend new items or new stuff to my customers. Whereas this one is essentially kind of finding out associations between different items in your data. Okay, so it's kind of completely a different class of algorithms. Okay, this is just some representation of those transactions. So here my transaction 1 contains 3 items: bread, cheese, milk. Transaction 2 contains apple, eggs, salt, and yogurt, and so on. Okay, the bunch of transactions, each containing multiple items. So each of this is an item, and the entire thing, the set of items, is called a transaction. Okay. Now, given this list of or data set of transactions, we want to compute rules like this. Okay, and okay, let's go and look at actually an example. So there are two measures that you use in order to figure out a particular rule is important or not. Okay, I can create any random rule, right? I can say bread implies iPhone. Okay, that means whenever I buy bread, I also buy iPhone. But that rule may not make sense at all, right? So I need some notion of kind of confidence or importance for given to a particular rule, so that I can kind of say that, okay, this rule makes more sense than something else. Okay, and there are two notions of measures. One is called support, and the other one is called confidence. Okay, support is essentially simply says how many transactions in my data support this particular rule. Okay, that means what percentage of transactions support the rule that I'm proposing. Like if I'm saying bread implies iPhone, how many transactions are supporting that particular rule, versus bread implies milk, how many transactions are supporting that particular rule. And obviously, intuitively, we will say that the support for bread implies milk will be much more than bread implies iPhone, right? That's obvious. And the specific way in which you compute that support is simply this. Okay. In this particular case, my rule is X implies Y. Okay. Actually, I think it's in the previous slide. Yeah. So the rule is X implies Y. And in our example, X is bread, Y is milk. Okay. So if I want to compute support of X implies Y, I compute like this: count of X union Y divided by N. N is the total number of transactions in your data. Okay. If I have Walmart database, I have, let's say, 10 million transactions by all the customers in my store. Okay. I take count of X union Y. That means how many transactions contain both X and Y. Okay. So I will see how many transactions contain both bread and milk together in the same transaction, I count all those transactions divided by the total number of transactions. Okay, it's essentially the percentage of transactions, right? Ratio or percentage. And that's why I said support of bread implies iPhone will be much lower than bread implies milk, right? Because if I look at my entire transaction database, there'll be a lot more transactions containing bread and milk as opposed to transactions that contain bread and iPhone, right? So that's the notion that captured by support, okay? And the confidence says our confidence in that particular rule, okay? Which means it's essentially, whenever I say bread implies milk, what is the confidence with which I'm saying that particular rule is true, okay? Which has similar to like a conditional probability. And that's essentially counted like this, okay? The numerator is still the same, count of x union y, divided by count of x, okay? That means in my example, if I am saying bread implies milk, count of x union y is count number of transactions with both bread and milk divided by number of transactions with just the bread, which is the left hand side, x, okay? That means out of all the transactions in which bread occurs, what is the percentage of transactions in which milk also occurs? That's exactly what it is capturing, okay? Count of x union y, that means count number of transactions in which both occurs divided by number of transactions in which only one occurs, okay? That's slightly different from the support. The denominator is different, okay? So those are the two things that you will compute in order to figure out the importance of a particular rule. And that's why in this example, we are saying this is my rule and this has this much support and this much confidence, okay? Okay, so let's look at an example actually. So in this particular case, these are my transactions, okay? Whenever you run your association rule mining, you provide two inputs. Apart from the data set, you provide two things called two thresholds. One is the minimum support and minimum confidence, okay? That means what is the minimum support you are interested in? What is the minimum confidence you are interested in any given rule, okay? So those are your thresholds. If you do not have those thresholds, there are so many rules that I can come up with, right? Something like bread implies iPhone, which totally do not make sense, and I don't want to see such bogus associations, okay? To avoid those things, I need to have some level of thresholds, okay? That means I want to see all the only those rules whose confidence is greater than 80%. And similarly, I want to see only those rules whose support is greater than 30% and so on, okay? So this is just some example, right? Here I have 7 transactions, beef, chicken, milk, blah, 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 blah. And if I have a rule something like this, clothes implies milk and chicken, okay? Support will be the union of these. How many transactions contain clothes, milk and chicken together? So which one is that? Clothes, chicken, milk. Clothes, milk, chicken, same thing. And then this one, right? No, where's clothes, chicken, milk? Yeah, exactly this one. So there are 3 transactions which contain the union of all. So my support is 3 divided by total number of transactions 7, okay? And the confidence means out of all the transactions in which clothes occurs, okay, where exactly cloth occurs? 5, 6, and 7. Okay, out of all the three transactions, I have both milk and chicken together, right? So my confidence is absolutely 100%. So that means whenever I tell you that a transaction contains clothes, with 100% confidence, I can tell that the transaction also contains milk and chicken. Okay, so that's the notion of confidence. It's a conditional probability. Okay, support is symmetric measure and the confidence is not. That means even if you reverse this thing, the support will still be the same, whereas confidence can change because your denominator is changing. Okay, so that's the high level introduction of the problem and where it's used. Okay, now let's see how to actually compute those rules very quickly. Okay, the most basic algorithm, probably people don't use it in the practice at all. Actually, maybe people might use it. It's a very basic algorithm, and that's the algorithm they proposed in the initial research article that they published, Rakesh Agarwal and others. It's called a priori algorithm. Okay, and even though it's basic, I wanted to show it to you so that you get the intuition behind this class of algorithms. Okay, it contains two steps. One is find all the item sets that have minimum support. Item set meaning a subset of items. So in this particular case, beef is an item set containing one item. Chicken is an item set containing one item. Beef and chicken is an item set containing two items. And similarly, beef, chicken, milk is an item set containing three items, and so on. Okay, so essentially item sets are all possible subsets over your entire set of items. Okay, so out of all those item sets, I figure out what are all the most frequent ones. That means whose frequency is greater than this support threshold. Okay, we are going to see an example. And once we find all those frequent item sets, you generate rules from those frequent item sets. Okay, so let's look at an example. This one. So let's say I have 4 transactions in my data. Okay, these are my transaction IDs: T100, T200, 300, and 400. And the specific items in this particular transactions are A, C, and D. They can be chicken, milk, and eggs, or whatever that is, right? Let's say those are A, C, D. And then the second transactions contain B, C, E, A, B, C, E, B, E, and so on. Okay. And let's say my minimum support is 0.5. Okay. That means I am interested in all those transactions, all those item sets and rules whose frequency is greater than 50%. Okay. Now, the way you compute the first step, which is finding all the frequent item sets, is going step by step. Okay. In the first step, you look at all the single item sets with one item. Okay. So my C1 is the set of all items with set of all item sets with a single item. Okay. Obviously, what they are? Individual items, right? A, B, C, D, E. So those are my item sets. Item set with single item A, item set with single item B, item set with single item C, and so on. And for each of that, I can count how many transactions are there. Okay. So for A, there are 2 transactions. For B, there are 3 transactions. For C, there are 3 transactions, and so on. And I'm interested in minimum support of 0.5. That means I need to have at least 2 out of 4, right? Since I have 4 transactions, my 0.5 times 4 would be 2. And obviously, by looking at these counts, I can see that D is no longer interesting for us, right? Because D has only support 1, that means it occurs only in one transaction. which is less than my minimum threshold, I no longer interested in D. Okay, so that's why I crossed it out. So as a result of that, I get this F1, which is frequent one item sets. Okay, which are A, B, C, and E, and they are called frequent because their frequency is greater than my threshold. Okay. Now, you can make one important observation, which is, so we say we crossed out D, right? Because it's no longer frequent. Its occurrence is so low that we don't care, right? Now, the next step of the algorithm tries to create two item sets. Okay. Now, just think about it. If D is not frequent, can AD become frequent? So, if milk is not frequent, can bread and milk be frequent? That means if D occurs in 20% of the transactions, which is less than, let's say, our 50% minimum threshold, can adding more items to that item set, that means A and D, can that frequency be more than 50%? No, right? It will be still less than the D's percentage. Does that make sense? If D is not frequent, that means it's not occurring enough number of times. Even A and D cannot occur enough number of times, right? Because by adding more and more items to the item set, your frequency will only go down. It will not increase, right? That's why I can remove everything related to D from now onwards. I don't generate, I don't consider A and D, B and D, C and D, and so on. Okay? Essentially, the algorithm is you start with one item sets like A, B, C, D, E, individual items. You cross out all the infrequent ones. In this particular case, D, you remove that. You get A, B, C, E. Okay? And then you take all possible combinations of these four item sets. Okay? Then you get these combinations. A, B, A, C, A, E, B, C, B, E, and C, E. Okay? These are all your candidate two item sets. Okay, that means item set with two items in it. A and B again can be like bread and milk. Now again you scan your database, your T transaction set, and then provide counts for each of these items. A and B occurs in only one transaction. So my count is 1. And A and C occurs only in 2 transactions, so my count is 2, and so on. And again I will see that, oh, okay, this one is occurring only once, which is less than my minimum support of 2, so I cross it out, I get my frequent item sets to be these 4, whose count is greater than or equal to my minimum support of 2. Okay, and using these item sets, I create all possible combinations and I generate 3 item sets. That means item set with 3 values. And in this particular case, I can only generate one 3 item set, which is BCE. Okay, which combines these 2. And again, I scan my database to see its count, which is again 2. So it's greater than or equal to my threshold. So I consider this also as frequent. Okay, so that's my first step in the algorithm. Compute all the frequent item sets, and whatever is shown as blue are all the frequent item sets. Okay, not blue, bold. Okay, once you compute these frequent item sets, you generate rules from these frequent item sets. Okay, so that's like the high level description of the algorithm to compute these association rules. Okay, so I understand that I'm going very fast for this algorithm. All I wanted you to understand is simply just acknowledge that there exists a class of algorithms called pattern mining algorithms, which are essentially kind of dealing with these frequency-based methods, and they're used in so many things, including retail industry and so on. Okay, so tomorrow in your interviews, if somebody says, do you know item set mining or market basket analysis and something like that, you can say, oh yes, I'm familiar with it. I know the basic setup and basic algorithm. Okay, and in this example, Sanchit says, why can't item A be used to construct item set with 3 items? Okay, give me an example. Which one do you think is a candidate? ACE, let's say, right? ACE, can this be a candidate? Now, think about it. If ACE is a candidate, then AC is also candidate and AE is also candidate, right? That means if ACE occurs 50% of times, then obviously AC should occur at least 50% and AE should also occur at least 50%, right? That's, I mean, just intuition. Now, as you can see here, AE does not actually occur 50% of times. So, ACE can never occur 50% of times. Okay? So, that means in order for something to be a candidate, all its subsets should be frequent. Only then something can be a candidate. Okay? And that's why you don't generate ACE in this particular case. Okay? The other slides which I did not show should give you complete information, but I didn't go over the class because you can take a look at them if you are interested in it. But I just wanted to give you a high level idea. And in Mahout, now getting back to Mahout, if you again type simply Mahout, there is something called FPG, which is frequent pattern growth, which is one particular algorithm to compute these frequent item sets. So we just saw this a priori algorithm here in our slides, a priori algorithm, and frequent pattern growth is another algorithm to do the same thing, which is more efficient. Okay, and you can use Mahout to compute those association rules as well. Okay, I can put up the complete data set and the list of commands that you would invoke in order to run frequent pattern mining algorithm in Mahout, which you can take it as a homework or to do at your home. We may not be able to cover it, but yeah, it simply shows a list of commands to execute here in order to compute association rules. Okay. So with this, you have basically learned yet another tool in machine learning toolbox that you are trying to build. So far you learned about clustering, you learned about classification, you learned about recommendations, you learned about pattern mining. Okay, so these are all like different tool sets you have in your hat. Okay, so again, the goal of this class is to kind of introduce you to different classes of or different sets of algorithms, which you can then go ahead in your business scenario and try to figure out, oh, which algorithm makes more sense in this particular setting. Okay, and in order to do such analysis, you need to be able, you need to first of all be aware of all the types of algorithms. Okay, and that's why I'm kind of introducing you to different type of algorithms here. Okay. Okay. So what is k-means, right? We have a data set, and let's say we have some initial set of clusters. Okay. Otherwise, you don't have anything other than D. So D is your data set. Okay. And C is your cluster centers. Okay. Initially, you don't have anything for centers, but let's say you randomly picked k centers. In this case, k is equal to 3. Okay. So you have a data set and you have a set of cluster centers. Now you need to iterate over our data set to update our cluster center C. Okay. Now, if you think about the algorithm, just remember what that algorithm is, k-means algorithm, right? The first and foremost thing that I need to do is the distance computations. I need to compute the distance between every data point and all the cluster centers, right? So for data point 1, I compute distance between D1 and C1, D1 and C2, D1 and C3. And similarly, I compute distance between the second data point D2 and C1, D2 and C2, D2 and C3, and so on. Okay. So I need to compute this all pair distance between the data points and the cluster centers. Okay. That's the first and foremost thing, and probably the most expensive one. Okay, because there's so much computation involved in it. I need to scan through entire data set, and for each record, I need to compute k values, which are k distances. Okay. Now, imagine how would you, think about it. How would you do this in MapReduce? Now, as we already know, mappers are essentially some independent pieces of computations, right? So you kind of divide your data set into different parts, and then each mapper will process on a different partition of the data. And if you think about the first step in k-means, which is about the distance computation, you can easily parallelize that by simply dividing the data set D into, let's say, D1, D2, D3. Okay, that means D1 contains first subset of data points, D2 contains other subset of data points, D3 contains the last subset of data points. So I divided my data into 3 parts. Okay, so let's say the first 2 rows, second 2 rows, and the third 2 rows. Okay, so that's my partition of the data. Now, each mapper will get a portion of data, and they can compute distance between those data points and all the cluster centers. Okay, so that would be the job done in a particular mapper. Okay, that's simply, essentially, I'm parallelizing the computation of distance computations. Okay, each mapper is computing some distances, and in union, I get all the distances between the data points and the cluster centers. Okay, so that's the way I would parallelize the first step in the k-means using mappers. Okay, is that clear so far? So I still did not talk about the key value pair, which is the actual representation of the data, which is also important. But the first step is to even computational organization of the entire algorithm. Okay, so the first step, as we discussed, would be to divide the data set into D1, D2, D3, which Hadoop is going to do for you automatically. So you don't need to do anything about it. Okay, now each mapper will take D1 and the entire cluster centers. C is very small, right? It's only k. If I want 10 centers, then I have 10 points, which is very small. So I can give it to every mapper, meaning I can replicate on every mapper. So in the mapper 1, I compute the distances between D1 points and the cluster centers. And the mapper 2 will do the same thing on the second partition that it has. Mapper 3 will do the same thing on the third partition it has. Okay? And I get bunch of distances and the nearest centers. Okay? Which I can kind of combine in the reduce phase. So I get some partial result from mapper 1, mapper 2, mapper 3. I get all this information in the reduce phase, and then using this information, I can compute the new set of clusters, okay, which is like doing the second part of the k-means, updating the cluster centers using the distances, okay. So this is how a map reduce computation would look like for one iteration of the k-means. All I need to do once I compute the new cluster centers is simply to repeat, okay. So every iteration of k-means is equal to one map reduce job. If I want to run for 20 iterations, I will run 20 map reduce jobs, okay. So whatever code I will put up on LMS for k-means, the map function is essentially be implemented in R, which is doing this computation of distances and computing the partial results. And then reduce function will also be doing the aggregation of these partial results to get the new cluster centers. Okay, that's like the high level description of map reduce way of doing k-means, or one possible method of doing it. There may be others as well. Now, with this, if you look at the code that I'm going to upload, it should be much easier to read through the code. The only thing that you know is mappers process data independently on different chunks of the data, and reducers will kind of combine these partial results into some result. Okay, that's the aggregation step. Now, given an algorithm, let's say naive Bayes or random forest is a little different, but naive Bayes or recommender engine or anything, you need to think about how can I find these independent pieces of computation which I can put them in the mappers, and then how do I combine these partial results in the reducer. So it's all algorithm based, right? Partitioning the data to implement map reduce is especially important, exactly. So you need to think that whatever mapper is doing is operating on a partial set of data or a partition of data. Now, how can now you have to decide what to do in that partition of the data, and then how to combine that result in the reduce phase to get the thing that you want to do.